of Sciences. I am Bassam Shakhashiri from the National Science Foundation. You'll have to forgive my hoarse voice. I've been suffering from a head cold for the past 3.5 days. And as my colleagues at the National Science Foundation will attest, I haven't been to work for 3.5 days. So I made a special point of coming out of bed to do this tonight. I hope you'll bear with me as we go through some the experiments tonight. I promise you a great deal of fun, and I hope you will learn as we go along doing a variety of special experiments in the tradition of a great scientist, Michael Faraday. I think everyone who has come into the auditorium has received a copy of the green pamphlet. I'd like you to read this, not now if you haven't read it yet. And I'd like to also point out to you how important it is for each one of you to pay very close attention to what's going to happen. Because in science, a great deal happens, sometimes very fast, and if you're not very attentive, you'll miss it. So I want you to be very, very attentive, and if you need some help, you can always call on your mommy to come and help you. No, seriously, I want you to be as attentive as possible, to pay special attention to color changes, to smoke, to noise, to a variety of things that might happen, and try to make as many observations as you possibly can and try to make some sense out of these observations. Before I go any further, I just would like to make a special tribute to the National Academy of Sciences for hosting this special occasion for the second year in a row. I don't know if Dr. Press is in the audience. Frank, could you come up here for a minute, please? Yes, you. This is Dr. Frank Press, the President of the National Academy of Sciences. Frank, it's my pleasure to present to you and to the Academy Volume 1 of my chemical demonstrations series and Volume 2 just hot off the press.
Terrific.
And I'd like to, if I may, read the dedication in both volumes. It says, "The Frank Press and the National Academy of Sciences, with appreciation for your continued support to science education. Bassam Shakhashiri, December 19, 1985.
Well, thank you, Bassam, very much.
Thank you, Frank. Now I'd like you to sit back and relax and try to enjoy what is about to happen. I want you, as I said, to be very, very attentive and to make sure that whenever we do experiments in science, we observe and obey the safety regulations. And I want you to know that I'll have my eye protection on throughout the evening as I do experiments. And I'd like you also to see the fire extinguisher that I have available here, just in case an accident happens. I hope no accidents happen this evening, but if they do, we are prepared to deal with them. Now, I'd like to talk to you a little bit about chemicals, because chemicals are all around us. The food that we eat is made up of chemicals. The air that we breathe is a mixture of chemicals. The medicine that we take when we're sick is nothing but chemicals. Our own bodies are made up of chemicals. What goes on inside our bodies, inside all the organs in our bodies, is nothing but a set of chemical reactions, biochemical reactions. And so it's extremely important for us to understand the properties and the behavior of a variety of chemicals so that we can enjoy the benefits of these chemicals as well as be aware of their potential hazard. We should be very, very careful in handling all chemicals, and you'll notice this evening and every time anybody does experiments, we should be carefully obeying the safety regulations. I'd like to, in keeping with what I just said, point out that there are quite a few chemicals that we deal with. Here's a carton of milk. Here's a can of Coke and some 7-Up, and a variety of other chemicals that can be readily found around the house. And these chemicals have different properties. One of the themes that we're going to deal with tonight is the so-called acid-base property of substances. So we're going to be looking at the behavior of some substances, their acidic properties or their basic properties. Now everybody has heard about the pH scale. You see television advertisement dealing with the pH of shampoo or the pH of different substances. And their pH is nothing but a measure of how acid or how basic is a substance. And there are a number of take-home experiments that I'll tell you about later that I'd like you to think about doing in terms of looking at the acid-base properties of these chemicals. It turns out that there is a way, there are several ways actually, in which we can test whether a substance is an acid or a base. You've all heard of the acid test. You've all heard of the litmus test. Well, what I have here are two pieces of litmus paper. If you just look at the monitor, you can see that they are of different colors. One is blue litmus paper, and the other one is a so-called pink or red litmus paper. The blue litmus paper, which is in my right hand, this will turn red if the substance that we are trying to test is an acid, and this pink or red litmus paper will turn blue if the substance that we're trying to test is a base. And the one thing that we want to try to do to begin with is test whether milk is an acid or a base. So we take some milk out, and what we need to do is test with this paper. What I do is, you just watch what I'll do here. I'll take a drop and put it on the litmus paper to wet the paper. Is there a change in color? Can you see any change take place? Well, you have to be careful, you see, because sometimes you think you see a change as the paper becomes wet. So you have to distinguish the wetness of the paper from a color change. Let's take the other paper and put some milk on it too. Is there a change there? It's pretty hard to tell. You see on the monitor, but it's much more easily the case if you look at this up close. And this is one of the experiments that I will give you some more instructions about doing at home. You'll be able to tell whether the milk is an acid or is a base. You can do the same thing with a variety of different chemicals that you can find at home, and you have to be very careful not to mix the chemicals that are edible with those that are not edible. For example, here's some, what's this? Household ammonia, and you've got to be careful not to mix those. We'll take some ammonia, we'll set it up here, and we'll go to see if we can find some more litmus paper to apply the acid test. And once again, we get two pieces of paper. I'll just set them aside like so over here. And I want you to see I'm just drying this, and I want to use the other end. Okay, so I take a little bit of the ammonia, and I take this paper, and I touch it. Is there a change in color? Yes. What's the color change that you see? So the litmus paper turned blue or violet, right? And that tells us that the ammonia is a base, because this pink or red litmus paper, when it turns blue, that means the substance is a base. Let me show you the same thing with the other piece of litmus paper. And you see this one simply gets wet. Well, this is the kind of experiment that you ought to try to do at home. I'll give you some more instructions about doing that at home. There are other ways in which we can measure the acidity or the basicity of a substance. There is something called pH paper, and I have samples of pH paper over here. I'd like to show you a close-up of that. You see there's there are different colors that this paper will turn depending on the pH of the liquid or the solution that we're dealing with. And if you have access to such paper in school, or your teacher can provide you with some, you might as well do the experiment with the pH paper, because that will then tell you the exact acidity or basicity of the liquid that you are dealing with. There's still a more sophisticated way of measuring pH, and this way is a so-called electrochemical method. It uses an electrode, and what you do is you dip the electrode in the liquid that you want to measure, and you hook it up to a meter, such as the one that you see over here. And it's not on. Is that on now? Yeah. Okay. And what you try to do then is to measure the pH value of the liquid. Now, I have to tell you that there is something mechanically wrong with this device that I'm using, because the pH of the liquid that I have in this beaker should be close to 7. It should be about 6.5, 6.52, 6.53. Actually, it reads 16.53. The 1 is erroneous, and that's on my display right in front of me here. The 1 is flashing, indicating that something is wrong, and that's why I can't show you the actual pH values of these different liquids. However, because in science we like to do experiments, I'm going to do this as an experiment and find out if we can, if this device is simply off in the 1 decimal place that we're talking about here. So I'm going to take this milk and try this. Turn this off. What's the reading now? It's even worse, right? That should be a 6 point something or other. Something is drastically wrong here. So we can't rely on this measurement, but we will take this. And where did we have the ammonia? Which one was the ammonia? This was the ammonia, right? Let's see what the ammonia does. If I take the electrode, put this on standby, turn this. So this demonstrates, we know that the ammonia is basic. It's demonstrated that this device is not working very well, and therefore we shall turn it off and move on to do something else. There are a variety of items in the home that you can test to find out if they're acidic or basic. It turns out that most of the household items that we can consume, that we can eat, most of them, not all of them, most of them are acidic. And the ones that we don't eat are basic. Not all of them, but most of them. And this is the kind of experiment you should be able to try to do at home. You know, there are many things that we eat that are not acidic. For example, when you take an antacid, obviously you're taking something that will counteract the acid. And so if you take milk of magnesia, for example, you will be taking something that will counter the effect of the acid, and it will be basic. So that would be one of the kinds of things that you might test the pH for at home. Now, there are ways in which we can tell, additional ways in which we can tell that a reaction is an acid reaction or a basic reaction, and that is by using a different set of color changes. Litmus is one type of indicator, and what I have at the lecture table over here is a set of different acid-base indicators. And the way in which we can tell that a reaction is taking place, if indeed it is an acid-base reaction, is to see if there is any color change. Now, I've arranged these different cylinders and beakers in such a way that the cylinder on my right with the beaker to its immediate left has the same liquid in it. So we'll use the color of what's in the beaker as the reference point always in the pair. And what I will try to do now is handle a very cold chemical this chemical is solid carbon dioxide. I'll put some over here. You can look at it on the monitor. This is dry ice, which is solid carbon dioxide, and it has the property of changing directly from a solid to a gas. That property we call sublimation. It just undergoes this direct change, which we call sublimation. But carbon dioxide, when it reacts with water, produces an acidic substance. So we're going to take chunks of dry ice, and I'm wearing, by the way, this glove to protect my hand from this very cold carbon dioxide. The temperature of carbon dioxide is minus 78 degrees Celsius. You know, in science, we keep track of temperature on the Celsius scale, and the sublimation point of carbon dioxide is minus 78 degrees Celsius. So I'm going to take a chunk of dry ice and drop it in here. We'll see what happens. Lots of interesting things begin to happen. We'll drop some more here. You see any changes take place? The color has changed. Look at this color changing over here. These are different acid-base indicators, different than litmus. And they change color as the carbon dioxide reacts with the liquid that's in each of the cylinders. And the color change depends on what's in each cylinder. The same thing would happen if I were to put the dry ice in each of these beakers. But remember, we left the beakers to tell us the original color of the liquid that we had in there. So carbon dioxide reacts with water to give us an acidic solution, and carbonated beverages have a great deal of dissolved carbon dioxide in them. I'm going to try to show you how much carbon dioxide there is in a typical can of 7-Up. So what I'm going to do is take this baby bottle, and this baby bottle has been fitted with a very special cap that has a hole in it. Through this hole, I've put a medicine dropper, the rubber bulb of a medicine dropper, and I'll show you that this is a very hard piece of rubber. I'll take it out and try to blow it up. You see, I can't blow it up. It's very, very hard. I'll put it back in. And what I'll do is open this can of 7-Up. Did you hear that noise? You've all heard that noise, right? That's the carbon dioxide escaping. I'll put this in the baby bottle. And the next thing I'm going to do is close this off very tightly and then shake it up a little bit. And you begin to see what's happening to this rubber ball as the carbon dioxide comes out of the 7-Up. The pressure of carbon dioxide that's dissolved in the contents of the 7-Up can is relatively high, and you could see I couldn't blow it out, but here's the effect of just a little bit of 7-Up in that baby bottle. Now let's do a couple of other experiments. Once in a while you might want to look back here and see if there's any further color change. It's a very colorful kind of an experiment. Here's another experiment that you might want to do at home. Actually, this is such an easy experiment. All of these experiments are easy if you know what you're doing. And you always have to be paying close attention to the person who is helping you do those experiments. In that regard, I'd like to get a volunteer from the audience. Can I see I have too many volunteers. I'll tell you what. There is a person who at one time indicated that she would like to help out in doing these experiments. And I'd like to call on Jan Watson to come and help me. Jan, want to come out and help? Come on up here. No, you're not too old. This is a very simple experiment that Jan will help out with. Here's a pair of goggles for you, all right? What we're going to do is take some, what's this?
Baking soda.
Baking soda. We open the baking soda, and we'll just add a little bit of baking soda in there, right? We're measuring this very carefully, right? You can see that, right? Next thing I'd like you to do is take this and stir it up. See if you can see what happens when you stir it up. Oh, don't be afraid. Just stir it up. You see the baking soda, which has been added to the water. What's happening to it? What's happening to it, Jan?
Dissolve.
Is it a clear solution?
I don't know. My glasses are.
Your glasses are. We can look at the TV monitor over there and see. Is it clear?
No.
It's not clear yet. Okay. Keep stirring and see what happens. The next thing that we're going to do is take some spaghetti. Right? This is something you can find at home, right? And you take the spaghetti and you the spaghetti into small pieces, about 2.5 centimeters. How many inches is that? About, yeah, 2.5 centimeters, like so. Okay? Is it clear now, Jan?
Sort of.
Sort of, she says. All right. Very, very good. Now the next thing what I'd like you to do is take these pieces of spaghetti and drop them into the beaker.
All of them?
All of them, yeah. Be careful not to bump this because this might, just blow up. All right? So now we've put the spaghetti in the beaker. What happens to the spaghetti that has been added to the beaker that has in it the dissolved baking soda?
It's clear.
It's, okay, the liquid is clear, but where's the spaghetti?
On the bottom.
Can you hear what she's saying? Yes.
Brilliant.
The spaghetti is on the bottom. So what does that tell us about the density of the spaghetti compared to that of the liquid? Is it heavier or lighter?
Heavier.
It's heavier, right? All right. The next thing we're going to do, she's going to do, is to take some vinegar. Right? You've handled that before. We'll open this. And what I'd like you to do is add some vinegar very slowly to the beaker and see what happens. Okay, that's good. Now, what do you see happening?
Spaghetti is rising.
Spaghetti is rising, she says. Okay, what else is happening?
And the water's bubbling.
And there are bubbles in the liquid, right?
Uh-huh.
So let's just watch and see if anything beyond this happens. What happens if I stir this up a little bit more? The vinegar reacts with the dissolved baking soda, and it releases a gas. These gas bubbles that you see are carbon dioxide bubbles. And if you look very carefully, near the bottom of the beaker, you can see, let me take this out of your way here, you can see it on the TV much better. You can see the spaghetti strands, can you? Not that easily, right? Well, let's add a little bit more. Is it okay to add a little bit more? All right. She says it's okay. We'll add more. And we'll let this experiment go for a little bit and see if anything happens to the spaghetti that is at the bottom of. You can see some of the spaghetti beginning to stand up, right? Oops, I keep pushing this thing in the way. All right, so let's see what else we can do with carbon dioxide. And what I'll do is I'll bring in this is how some of us wash dishes at home, right? What we're going to do, Jan, is ask you to put this glove on and take some of the dry ice and simply put them in there. See what happens.
How do you do it?
It's pretty hard to pick them up. Yeah, just dump it in there. Okay, dump some more. Tell you what, why don't you just take this whole thing and dump a few in there, okay? That'll be easier. Okay, that's good, thank you. And now you can you blow on it a little bit? Just blow on it, blow on it.
Like Macbeth?
It's like Macbeth, right. What this is condensed water vapor. What I had in the trough, I had some water, some warm water, and we simply put some dry ice on top of it, the same kind of experiment we did over there, except that the water was warm. And what you see is the condensation of water vapor on the carbon dioxide that's escaping to the atmosphere. And this is the way, this is one of the ways in which they make smoke sometimes in the movie. Well, thank you very much for helping out. Give her a hand for helping me out. Wasn't so bad, was it? Okay. Now, what I'd like to do is move over to a different kind of experiment, an experiment that deals with this reaction. Everybody's carried out this reaction at one time or another. You take a match and you strike it. It's no big deal, right? Actually, it is a big deal because there's a lot of chemical change taking place there. There is heat released, there's energy in the form of heat, there's energy in the form of light, and the match is burning very fast. In fact, if I don't blow it out very quickly, I'll burn myself, right? So this process that we're dealing with here is called combustion. This is an example of what we refer to as controlled combustion. When a combustion process goes out of control, then we have what we refer to as a very fast reaction, and we call it an explosion. What I'd like to show you now is the way in which we can use a different source of energy, namely a propane tank, to carry out a combustion process using a burner. Here's another example of controlled combustion. That's me.
That young man?
I am he.
And have you been a good boy this year?
I think so.
Well, good. I'm glad to hear that.
You have to ask Mr. Block. Is Mr. Block here?
The next question I have for you, have all these boys and girls come to learn some science from you?
I hope so.
Well, I am so pleased about that I have brought some presents for them and for you. Now let me see. It's down here in my sack. Yes. Here it is. I have an envelope here.
Uh-oh.
It has in it some litmus paper.
Oh, good.
Now, I didn't bring you any electrical pH meters because I understand they don't always work.
That's right.
But I did bring you some old reliable litmus paper and some other things. Perhaps you will. And I have an envelope like that for each of your visitors here this evening.
Well, that's very kind of you, Santa.
And I wish to each of you a very Merry Christmas.
Thank you very much, and the same to you, Santa. Thank you. Thank you. Can you stay, Santa, and watch the rest of this? Okay, sure. Let's take a look and see what's in Santa's bag in here. Well, I see, I'll just put what's in there. I see lots of pieces of litmus paper for you to work with. I also see a button that everybody can get. Can you read that? Right, just like the button I have. I also see a very small disc. I don't think you can read that on the camera, but I'll tell you what it says. It says, discover excitement, jump into science. That should give you a clue as to what this disc will do. There's a set of instructions for using this disc. The heading on the instructions is jumping disc. So that's a clue for you. There are two dark pieces of polarizers. I'll tell you about those a little bit later. Santa anticipated one of the experiments I'm going to do. And then there is a light stick for everybody to do experiments with, and a set of instructions to work with the light stick. And finally, there is, this is the part you have to pay very close attention to. There is a blank gummed label. This blank gummed label is for you to write your name and address and send it to me so I can send you a full set of instructions for doing many of the experiments that we're doing here today, free of charge. All you have to do is write your name and your mailing address on this gummed label and send it to me, to the National Science Foundation, and in a couple of weeks, right after the Christmas rush, we'll give you a set of instructions for doing some of these other experiments that we've talked about. Okay, so as you leave tonight, each one of you from Santa and from Santa's helpers will be getting one of those envelopes. Is that right, Santa? That's right. That's right. Okay. So let's move on with this experiment that we were trying to do over here. This experiment that deals with combustion. This is the combustion of propane, and it releases energy in a lot of different forms, heat being one of them. And the other one, of course, is the emission of light. We're going to try to use this source of heat to heat up this can. Now, what I'd like you to do is to listen very carefully to what might be inside this can. Do you hear anything? There's a liquid sloshing around, right? What we're going to do is heat this liquid. I'll tell you, this liquid is water, and we're going to heat this. And how do we know that water boils? What do we look for? Bubbles. We look for bubbles, but it's pretty hard to see bubbles inside this can, right? What do we look for? Steam. Well, you know, we look for steam, but actually what we see is not steam, because steam is an invisible gas. What we see is condensed water vapor, and so that's what we ought to try to look for near the top of this can. There's an opening over here. I'll show it to you without burning myself. There's an opening right there, and we'll watch to see if any condensed water vapor comes out of that can. Make sure this is sturdy. Okay, let's take a look back at the spaghetti that Mrs. Watson was helping us with. And I don't see too much happening to this spaghetti. Just shake them up a little bit. And we'll see what happens, if anything happens. That's why we do experiments, to find out if anything is in fact taking place. We look for changes, as I told you, in color and in other properties that we are dealing with. Now, I told you one of the themes that we're dealing with is acid-base chemistry. Now, what I'd like to do is carry out a different kind of an experiment, which indeed is an experiment, see if it works out. This experiment I'm going to do on the top of this piece of cardboard right here. And what I'm going to do is take a couple of crystals of a solid, just put them on top. And the next thing I'm going to do is take this liquid out of this flask and pour it on top of this cardboard where the crystals of this solid are, and we'll see what happens if anything happens. And you see we changed the liquid that was inside this flask into this crystalline form. What this was a supersaturated solution of a substance we call sodium acetate, and it crystallizes in this form the minute that you put a seed of crystal sodium acetate in it. That's what I took out of this bottle, and that's how we can do this experiment. If I had a steadier hand, we could have made a much longer column out of this. And by the way, this can be reused by putting it back into a clean beaker and heating it, not adding any liquid to it, just heating it until it dissolves again in its own water of crystallization. So this is sodium acetate trihydrate. Let's take a look at the can. You see anything coming out of the can? What do you see coming out of the can? It's condensed water vapor, right? You can't see steam. So this can is getting pretty warm now. And what I'm going to try to do is take the can and I'm going to stopper it using this rubber stopper, like so. I'll take it off, put the rubber stopper on, and put this in some ordinary ice, okay? Just ordinary ice. Just watch the camera. And cool it down. You can see what's happening to the can. The can is collapsing. The can has collapsed once I put this stopper on. And the question is, how come the can collapsed once I put the stopper on? Because I pushed it? Very good. I'll tell you what. I'll try to push it some more and see if I can make it collapse, okay? And I'm pushing pretty hard on it. I can't make it collapse as much as it has collapsed so far. So I didn't push it. Something else pushed it, right? Who did? Who pushed it? Some invisible giant of some sort? Right? Let's stop and think of what happened to this can. We had a little bit of water in it, and we heated the water, and the water came out of the opening, right? When the water vapor was coming out of the opening, it was sweeping along with it some of the air that was inside the can. When I put the rubber stopper on the can and closed it off and then cooled it back down to close to room temperature, then the can collapsed. The conclusion that we come to is that the pressure inside the can was different than the pressure outside the can, right? And where is the pressure higher, outside the can or inside the can? Outside the can. Now, how did the pressure inside the can get to be smaller? It got smaller because some of the air molecules that were inside the can were swept along with the water vapor when it was escaping. And so this is the experiment of the collapsing can that shows us that the pressure of the atmosphere, atmospheric pressure, is a very real pressure and a very strong pressure. Now what I want to try to do is to change this burner and go to this burner and see what happens as we carry out another controlled combustion experiment. Again, using propane as our fuel. And you see now this flame is different in color than the flame that we had in this burner. And one of the questions we should think about is, how come the color of this flame is different than the color of that flame? Is there any significance to the difference in the color? Those are the kinds of questions that we always try to think about answering when we do scientific experiments. Let's increase the flow of the gas. And you see, no matter how much I increase the flow in this burner, the color of the flame remains yellow. Now, what we've learned so far, I hope, is that some substances undergo controlled combustion. There are many substances that do not undergo combustion. They don't burn. Combustion means they combine with oxygen and give off energy in the form of heat, in the form of light. Now, when you came into the auditorium tonight, you saw lots of different things on the table, including those balloons that are up in the air. I hope you noticed that these balloons are up in the air and they are on strings, right? So the strings are holding the balloons from floating farther up into the auditorium. What does that tell us about the gas that's inside each of these balloons? What? Helium. It's helium? You think it's helium? Well, I'll tell you. Helium is a gas. That's correct. It's also a gas which is lighter than air, which means that when you fill up a balloon with helium gas, the balloon will go up in the air. But helium happens to be a gas which does not undergo combustion. It means it doesn't burn. So one way of finding out what's inside these balloons is to put this flame right to the balloon and see if there is a combustion reaction. All right? You ready? Yeah. Let's do that. Let's take this flame and put it right to this balloon. And you see what happened? What happened? The balloon popped. Now, some of you are paying close attention, and that's why we are going to repeat this experiment using this other balloon. That's what we do in science. We repeat the experiment over and over and over, not only twice, but enough times to convince ourselves that the experiment observations are valid. So let's go and do this, being careful not to put the flame to the string, because if you put the flame to the string, what will happen to the balloon? How do you know that? Well, if indeed it has helium in it, see, I can put this torch, this flame to the string, and what will happen? How do we get to find out? Well, you see, when you do experiments, you have to decide which experiment you want to do. If you want to find out if the flame will burn the thread, you can do that experiment. I don't want to find that out. I want to find out what will happen up here. See, and the flame went out. So very quickly, we go like so. And indeed, the gas that was inside both balloons did not burn, and that gas is, or was, helium. Now let's try these other balloons and see if the same reaction takes place. You ready? Now, be careful in terms of the observations that you make. All right. Was that the same kind of a gas inside? Now, there were so many different things that happened in this combustion reaction compared to the other one. What is one of the differences? There was a lot of energy released in the form of, well, in the form of sound, right? Sound energy. You heard the explosion. There was also a big flame. And for those of you who didn't see the flame, what we're going to do now is repeat the experiment, but turn off the lights. So turn off the lights. Are you ready? Now, I told you that over there, I didn't want to find out if the thread burns. I really didn't want to find out over here either. Okay, let's go over to this one and see what happens if we're careful and put this like so. Actually, I want to just try to point something out to you, because I told you at the beginning it's very important to obey the safety regulations when we do this experiment, right? Now, you have noticed as one of your observations, which you haven't told me about because I haven't asked you, as we move from this side of the table to that side of the table, there are changes in the intensity of the combustion and the associated reactions going along combustion, right? Namely, the sound that is released. And so what I'm going to try to do, and suggest that you do too, is cover up your ears to protect your eardrums from the possibility of puncture. But I can't do that and do the experiment, so I have these earplugs. Okay, so I'll put those on. Now, if you can hear what I'm saying, you don't have your ears covered very well. And I can tell from your reaction, you're laughing, that you can hear what I'm saying. So cover your ears very well. Okay, all right. I'll tell you what, we'll do this experiment one more time in the dark, and I'll be very careful. So cover your ears. Now, what was inside the red balloon was hydrogen gas. Hydrogen gas is a very, very explosive gas if it comes in contact with a spark or a flame. What was inside the yellow balloons was a mixture of hydrogen and oxygen gases. And that's a very, very dangerous mixture. And as you could see and hear, if you didn't have even if you had your ears covered very well, you could still hear the room vibrate. I hope, Dr. Press, that this auditorium is still in good shape. And the combustion reactions that we saw demonstrate the explosive nature of hydrogen, and especially when mixed with oxygen. Let's get this sodium acetate trihydrate out of the way and carry out a different kind of a combustion reaction. This combustion reaction we're going to carry out inside this small plastic bottle that has 2 nails driven into it, but the nails are not touching. Why don't you show us a close-up of that? You can't see the nails not touching. And into this, I'm going to make a combustion chamber out of this by taking a little bit of a fuel. In this case, it's alcohol, ethyl alcohol, putting ethyl alcohol in there. And I'll do it with 2 of them. And then I'm going to stopper the small plastic bottle like so. And I'll tell you that these 2 nails are separated by about 1 to 1.5 centimeter distance. And what I'm going to try to do next is to see if the vapor of the alcohol can be ignited as I put a spark across the gap that we have between those 2 nails. And I'm going to put a spark using something that we call a Tesla coil, which I want to show you that there's a spark coming across from this. This is a dangerous kind of an experiment, and you should not play around with it unless you have had experience with it. And what I'm going to show you is the spark jumping from this coil one set of nails and see what happens. See that? Now you didn't sit. All right. You didn't sit because you weren't paying any attention, right? Let's do one more in the dark. That's why we repeat experiments. Let's do it in the dark. Yeah, let's see what happens. Now I can't see what the nail is. Okay, I got it. And you see the alcohol vapor, when the spark jumps from one nail to the other, is ignited and burns and releases a great deal of energy. Not too different from what happens in the internal combustion engine that we use, except that the fuel there is a different kind of a fuel. All right, let's do an experiment now right over here, where we have a very large beaker. This beaker has a volume of about 4 liters, and it has in it some water. Actually, it's getting a little bit hot here. I'm going to take my coat off. Is that okay to take my coat off? And actually, I'll take my tie off too. Is that all right? Okay, how about if I take my shirt off? Would that be all right? I promise you, Frank, this is all decent, so. Okay. All right. I hope you agree with this. I can tell from your reaction that most of you agree. Maybe all of you agree. Let's look at this 4-liter beaker. It has in it about 3.5 liters of water, and it's sitting on top of a magnetic stirrer. There's a spinning bar sitting at the bottom of the beaker, which you can't see very well. And I'm going to mix a couple of different chemicals from these 2 bottles into this beaker and see what happens. That's, again, why we do experiments. We mix things and we make observations and see if anything happens. The first one I'll mix, I'll just put a little bit of this. Nothing much happens. I add a little bit of this. Something is beginning to happen. I add some of this. You know, what's a much better way of mixing chemicals carefully is to use these medicine droppers, and that's what I'm going to try to do. You see anything developing down the middle? What is it? What does it look like? It looks like a tornado. What color is it? What color is the tornado itself? Green. And if you know what you're doing and you mix the right chemicals together, you can produce this effect right down the middle of the vortex, as it's called, that is created by the spinning bar in the liquid. See, if I add the solutions to the side, you don't get the same effect. You've got to add the solutions of these chemicals right to the center of the vortex to get this tornado effect. And you notice that the color now is what? Is orange, right? Okay, well, enough about that tornado. We can watch this for a long time, as long as the insoluble substance that's being formed stays in the middle of the vortex. And if we add one or more of the reactants, then we can make that insoluble substance disappear. You know, in science, especially in all sciences, we do experiments to find out what happens. And someone said, I don't know exactly who said this, but someone said that when a phenomenon occurs and everyone is capable of understanding what happened, we call that science. When a phenomenon occurs and very few people know what happened, we call that magic. You know, the magician knows all the magic tricks that are involved. And this person went on to say, when a phenomenon occurs and no one understands what's happened. We call that a miracle. Well, what we are interested in is science. We're interested in understanding what goes on, and I'll tell you that this is a mixture of mercuric nitrate and potassium iodide in the proper ratios to produce the insoluble mercuric iodide, which then eventually dissolves to form a complex ion, which happens to be soluble. So enough about that experiment. Was I turning off the wrong one? Is it on or off? Now I can see it now on my own monitor. Thank you. Okay, what we're going to do is add a liquid out of this bottle. You see, depending on the size of the bottle and the shape of the neck of the bottle and the opening, you can add things sometimes very quickly. Sometimes you can't add them as quickly as... I will leave that one alone. We'll just add some out of here. And we'll add some out of there. Okay, and what's the old saying? More is better, right? So we'll go and add a little more. Even a little more. Is anything happening? This is an example of what we refer to. Oh, I haven't put my microphone down. Got carried away with my T-shirt. You can still hear me, all right? Okay. This is an example of what we refer to as a chemical oscillating reaction. The colors oscillate from one to another. And if you've been watching this now for a little bit, you've been making lots of observations about this. Beyond the sequence of color change, I hope you've been making additional observations. For example, what can you tell me about, first of all, the sequence of the change? What is it? It goes white or colorless, and then a little bit of orange, and then it goes black, right? It's blue, actually, it's so deep blue, it's black. But what has been happening to the time that each color is lasting? Is that the same or is it changing? See, the blue color or the deep blue black color now is lasting much longer than before. And this is one of the properties of this reaction. I want you to know this is a very special reaction. It's so special, and I want to tell you about it. It was discovered by two high school teachers in 1973, and it was not until 1982 that a member of the National Academy of Sciences published the explanation for this reaction. That's Professor Richard Noyes from the University of Oregon, who published the explanation for this sequence of steps involved in this reaction. The sequence of steps actually has in it about 24 steps. But the two high school teachers discovered this reaction in 1973 and published it in the Journal of Chemical Education, which is an indication of how important it is to make observations and try to make some sense out of the observations and then come up with an explanation so that the explanation can help you control what happens to this chemical reaction. Okay, now let me move on very quickly to a different kind of a reaction system. And before I do that, I want to carry out one very special experiment because it is the value of experimentation that is what I'm trying to share with you tonight. Before I do that, I want to read to you a short quotation from Ira Remsen, who was a chemist at one time and later on became the president of Johns Hopkins University. And this is what Ira Remsen had to say. This is when he was a little kid. And if you pay special attention to this, you'll see the point that I'm trying to get across tonight. It goes like this. While reading a textbook of chemistry, I came upon the statement, nitric acid acts upon copper. I was getting tired of reading such absurd stuff, and I was determined to see what this meant. Copper was more or less familiar to me, for copper cents were then in use. I had seen a bottle marked nitric acid on a table in the doctor's office where I was then doing time. I don't know what that means, probably waiting for an appointment. I did not know its peculiarities, but the spirit of adventure was upon me. Having nitric acid and copper, I had only to learn what the words act upon meant. The statement, nitric acid acts upon copper, would be something more than mere words. All was still. In the interest of knowledge, I was even willing to sacrifice one of the few copper cents then in my possession. I put one of them on the table, opened the bottle marked nitric acid, poured some of the liquid on the copper, and prepared to make an observation. But what was this wonderful thing which I beheld? The scent was already changed, and it was no small change either. A green-blue liquid foamed and fumed over the scent and over the table. The air in the neighborhood of the performance became colored dark red. A great colored cloud arose. This was disagreeable and suffocating. How should I stop this? I tried to get rid of the objectionable mess by picking it up and throwing it out the window. I learned another fact. Nitric acid not only acts upon copper, but it acts upon fingers. The pain led to another unpremeditated experiment. I drew my fingers across my trousers, and another fact was discovered. Nitric acid acts upon trousers. Taking everything into consideration, that was the most impressive experiment and relatively probably the most costly experiments I have ever performed. It was a revelation to me. It resulted in a desire on my part to learn more about that remarkable kind of action. Plainly, the only way to learn about it was to see its results, to experiment, to work in the laboratory. And that's what I'd like to show you now, this experiment. Here's a copper penny. You come back over here, and what I'm going to try to do is take this copper penny, drop it into this flask, and I'm going to take some nitric acid and pour the nitric acid on top of the penny. You're beginning to see some change. I'll take this colored background away from. You see some change? That's the nitric acid acting upon the copper. The liquid is green, yellow-green, and there are fumes coming out. And because we want to obey the safety regulations, I'll take this stopper, put it, whoops, did I use the wrong size flask? I did. That's not going to work too well. The copper penny is dissolving, and the brown gas that you see coming off that is nitrogen dioxide, NO2. It's one of the pollutants that we have in the atmosphere. And as long as I'm careful in shaking this like so, very slowly, it will try not to have it escape into the room. The next thing that I want to try to do is to take, I want to try to stop the reaction by taking the contents of this flask, and you see there's several, you can't see the color. It's so deep red, it looks deep brown, I mean, it looks red. What I'm going to do is to try to pour this like so. And here we have a solution of copper nitrate and this is water. I just poured it into water. And this flask is still full of the NO2, which we'll try to keep in there until the end of the presentation. Now, very quickly, another set. By the way, what has happened to the oscillating reaction now? It just stopped, right? Whoops, I keep turning the wrong way. It's no longer oscillating because the chemicals that are being produced have been totally consumed, and the color that you see is the deep blue color of the starch iodine complex that has been produced. All right, a couple of other quick experiments before we go. These experiments cannot be done at home because you don't have the chemicals, although this first one can be. What I have is some acetone, which I'm going to put into this dish. And I'm shifting discussion now from talking about copper pennies and nitric acids and indicators and acid-base behavior into a different set of chemicals altogether. I'm going to take this cup of polystyrene, and what I'm going to do is put this cup into this acetone and see what happens as I put it into the acetone. And see, the acetone dissolves this man-made product. And that's what we do in chemistry. We can make some things disappear, but we can also make some things appear. I'm going to take a brown liquid out of a different styrofoam cup and mix it with an amber liquid out of a different styrofoam cup. And we learned tonight, I hope, that reactions don't take place unless you mix them, right? Sometimes they react right away. Sometimes you just have to mix them real well and wait and see if a reaction takes place. So you see, in chemistry, we can make things disappear and we can make other things appear. This is an example of a substance not too different from polystyrene. This is polyurethane foam. And this is how it's made, actually mixing those two reagents together. And this has a lot of different uses. It's mostly used for insulation purposes in a variety of places, at home, for example, or airplanes and so on. Unfortunately, one of the undesirable properties of this substance is that when it burns, it emits very poisonous gases, which can cause harm, in fact, can cause death. But I just want you to know that it's a very simple substance that is made in this fashion. Now, a couple of other experiments that I want to show you so that you can do them at home with what Santa Claus has brought. Well, one of the experiments has to do with using these two small pieces of polarizers. And what you need to do is to use a source of light, like a light bulb, or use a flashlight. And to show everybody what's going to happen, I'm simply going to use the overhead projector. And instead of your small 2 inches by 2 inches pieces that you have in the packet that you'll get, I'm going to use these larger pieces. Actually, what you should do when you get your small pieces of polarizers, you'll find that there's a small piece of protective film on them which you should peel off. And that's what I'm trying to do, peel this off. Need somebody with long fingernails. Okay, I got one piece off, right? And then the next thing you do is you peel it off the other side. And you do this with the 2 pieces of polarizers that you have. And then you get a piece of baggies or Ziploc, whichever brand you use. And you put one polarizer like this on the source of light that you have. And I'm going to use actually the big ones to have everybody see. And then notice what happens when the polarizers are parallel to each other. The light comes through. When you rotate like so, 90 degrees, the light will not come through. When you're at an angle of 45 degrees, some of the light comes through. The next thing that you do is you take this baggies, or you take any piece of film that you have. I'll take the piece of film that I just peeled off and put this right in the middle, like so. And I want to show you that you can see at the 45-degree angle, you can see, oh, here's another piece that somebody just gave me. Yeah. We'll put that in there. And you can see different light coming through depending on the angle that you rotate one of these polarizers to. Now that's all very much fun and interesting. This is a phenomenon called birefringence. But there's more that you can do with it. And since you were kind enough to help me with this, I want you to help me a little bit more. Can you hold this polarizer up like so? Just hold it up like this. And this requires 2 people. The next thing that you do is you try to stretch. If you stretch this and you have the focus done right, you can then get these very interesting color. Thank you. You can get this color development. And if you take a piece of plastic or a plastic cup like this, you can see the stresses and the strains in it between those crossed polarizers. So this is an experiment that you can do at home using those 2 small pieces of polarizers. It's one of the properties of the substances we call polymers. Now, one other experiment which I will describe to you and then let you do it at home. Inside each packet, you will find a rubber band. And the experiment you should do with the rubber band is the following. You put the rubber band close to your forehead or close to your lip, and you feel it. And you try to describe what you feel. Among other things you try to describe is the temperature of the rubber band. The next thing that you do, and I'll move sideways so you can see what I'm doing, move the rubber band forward and quickly stretch it and put it back on your forehead or on your lip. And then say or report what the temperature change is. The next thing you do after that, with the rubber band stretched, release it and put it on your forehead, and again report what the temperature is. You will observe a change in temperature as the rubber band is stretched and as the rubber band is released. And this stretching and releasing of the rubber band is related to the properties that the rubber band has. And all of these instructions will be in what I mail you out once you send me the set of instructions, once you send me the gummed label for the set of instructions. Now, the other experiment I want to try to do, which is not in your handout, is to take still another balloon, blow up this balloon like so, release the air just a little bit, and then tie the balloon to demonstrate still another property of this rubber. What I will do is take a very sharp needle, and I want you to come as close as you can. This is a very sharp needle. You have to be very careful in handling this needle. And what you do is you take still another chemical, or a mixture of chemicals, in this case some Vaseline, and you lubricate this very, very carefully, moving in the right direction not to hurt yourself. And then the next thing you try to do is to put this needle through the balloon without having the balloon puncture. So let's see if we can do that. I know we did that last year, right? So let's see if it'll work this year. Those of you who weren't here last year and see the balloon still there, right? And there's actually a hole on both sides of the balloon. I want you to listen very carefully. Just listen, just listen. See if you can hear the air coming out. Hear the air coming out? Yeah, there are two big holes here. In fact, the balloon is getting smaller, right? See the balloon getting smaller? And there's nothing really magical about this, because if I puncture the balloon, it punctures right away. Now, let's do this experiment one more time so that you can see exactly how I'm doing this experiment and how the magicians do it, and the next time a magician does it, you can explain what's going on, right? You blow up the balloon, you let some air out, you tie the balloon, and then if you look very carefully at this balloon, and you come up as close as you can in this with the camera, as close as you can with the camera, other than these reflections that you see. Do you see the spot right here? Right? Does everybody see this spot? This spot is thicker than the rest of the balloon, right? There is another spot right near the place where you blow up the balloon where it's also thicker. Now, if you put this needle, which has been lubricated to just make life a bit easier, if you lubricate this needle and you put it right through that thick part, which is what the magician does, okay, it'll go through. So come in closer. Can you see the thick part? Wait, you just stay put. I'll find it. I'll find you. Here it is. Okay, right there, right? What we'll do is go through this. You see it, right? And we come out the other end, and you see the balloon does not puncture. That has to do with the stretched rubber and this change in the thickness of the stretched rubber, where we can drive this very sharp needle through the balloon. And of course, when we get done, we can pop the balloon like that. Well, these are some of the experiments that I wanted to share with you tonight. I know the hour is late, and I know there are many other experiments that we could have done, and I'll try to do some of these again next year. You've been a very good audience. I want to thank you for coming. And don't forget, as you leave the room, get a packet from Santa or one of Santa's helpers and send me that information. Now, before you leave, can I have your attention for just one more second? There are two very special people who made all of these And I want you to acknowledge his help. That's Fred Juergens. Fred is over here. And the other person is a graduate student in chemistry at Georgetown University who also spent several days getting all of these things ready, and that's Ken. Ken, will you take a bow? Thank you and good night.